Okay, here we are. Welcome to the first uh, broadcast that we're putting on here. Don't really know what I'm doing, but converted the dining room into a little bit of a classroom. I've got my whiteboards here. Made a little thing to hang them on the wall so you can take more on or off or whatever we need to do. Stole my daughter's microphone from her karaoke machine, so hopefully that's all working. Um, figured for this first video we'd talk about this is where we're at, and then the second half would be this is where we're going, and talk more about the actual AP test or the modified AP test. Go over the specifics of that and talk about the example problems that they posted online to talk about each problem. So, yeah, so this is where we're at. School's closed for the rest of the year. Um, that's super sad. I miss you guys. It's weird, strange, confusing, all of the feelings. Not getting to see you guys. Thinking about the seniors and your senior year just kind of makes me super sad. Not going to talk about that because I'm trying not to cry on the first video here. Um, yeah, so we've got a long way to go to get us all there. Um, the main goal, I think, for us is just to prepare for the AP test. Um, yeah. Um, Also want to send out a super big thank you to any of your parents or guardians who are, in the medical profession or first responders and still going to work, taking care of sick people. They deserve all the feelings, all the love going out to those people. So if you have a mom or a dad who's a nurse or a doctor or an x-ray tech or a police officer or a fireman, just make sure, after they wash their hands and take a shower, give them a big hug when they come home tonight. So, yeah. Hopefully everyone's staying home and staying healthy. And, yeah, hopefully I'm going to start making more of these on a daily basis. This one's going to be talking about the test and the specifics, and then the other ones will either be kind of like lecture, demo, learning activity kind of things. I did go to school and get a bunch of equipment to do some demos and whatnot and try to film those for you guys. So we'll do that almost like a real class, or at least you can watch me do what I would normally do in class, and I'll just speak awkwardly at this camera um, while I also watch the birds in the bird feeder out the window. So that's distracting, just like class when you guys are talking and not listening to me. So, all right. Um, let's see. Anything else to talk about? Grades. Grades. Not totally at this point do we know where grades are going. It seems like from Superintendent Thiele's letter that since we're no longer returning to school and it's closed for the year, that grades will go pass fail. Not pass fail, pass no count for second semester. Um, I would think looking at my grade book, almost all of my AP students had a passing grade at the time of school closing. And so I would think as long as you engage in whatever online learning that takes place that's graded after spring break, that you should expect to pass this class. The other thing that came up today through email and some other AP teachers was talking about grade bumps and AP grade bumps. Refer to the syllabus, but just real quick, my grade bump policy is pretty straightforward. You have to get a 5 on the exam. You have to have done 80% of the homework in the labs to qualify for a grade bump. And it's pretty straightforward. You get a 5, you get an A in both semesters. I don't see any reason to really change that policy, even though second semester is obviously super wackadoodle and you'll get a pass, you won't get an A. But the grade bump policy will still apply to first semester, since the majority of the test is first semester material since they've cut out the last 2 units. So, okay, I think that's where we're at. So after this video, I'm probably going to make another one tonight with a fun problem about train tracks and different types of wheels. It's a really interesting question. It brings up some rotational kinematics, but then there's also a way to explain the question with forces and also energy diagrams. So it'll be a good question to do some review material as well. So that'll be the next video. That's where we'll kind of start off. And then in addition to me kind of putting together some demo lecture videos, I'll probably spend some time just doing some WebAssign problems on the board and explaining them, which is super kind of weird without you there to then ask questions in real time. So you'll have to probably just email me your questions. That'll probably be the most efficient way. I'm pretty much on email all day long with my phone in my pocket and not going anywhere. So even though after spring break we're supposed to keep official office hours, don't ever hesitate to just email me your question, and I'll get back to you as soon as I can, either just through emailing you back on the phone, or if your question I think requires a diagram, I'll draw a diagram up on one of the whiteboards and I'll send you that as well. So I'll have official office hours moving forward, but just email me your questions whenever you have them. Yeah, okay, so that's where we're at. All right, so this is where we're going. Been kind of reluctant to start doing these things because didn't really know where we were going, or what my actual, how do you want to say it, legal liability risk things were at until Issaquah School District and the union negotiated kind of more terms, what things could be put out there for students and what should be expected of teachers and students as we move forward. That's a lot more clear now as of last Friday, but then with schools being closed for the year on Monday, kind of complicates things again or raises more questions. Also, AP finally put out some very specifics about what the test is going to look like. So that's what we're going to talk about now. That's where we're going. AP College Board's given us a new target to hit, and the remainder of our time from now until May 11th at 9 a.m. when your test is, we got a target to aim for now. So that's what we're going to go for the next month. Let's see what to say about all that. The test is different, obviously. You're going to take it remotely. You're going to take it from home. You're doing it on a secure browser that College Board's put out there. Excuse me. There's links to the secure browser and how it works on my website, so check those out. Make sure you've downloaded the secure browser. You can access it and log on. There's a how-to guide. And College Board also promised that there would be opportunities to practice these style of questions and using the secure browser. If you've been doing the optional AP progress checks through AP Classroom, I think that's also a good, it seems like a good format to practice because you can either type in your answers or you can write out your answers and then submit a photo or a scan of your written answers. I think that's the way it works. That's the way the reading here kind of presents itself as well. So yeah, so here we go. Let's talk about the test. I got 3 documents in front of me. I've also linked them on the website next to this video. So if you haven't printed those out or taken a look at those yet or have them up on your computer as you watch that, I'd suggest you pause this video and either pull those up online or print them out so that as I talk about them, they make sense. My video editing skills are not good enough to have them show up and highlight and whatever as I talk about them. So the first thing we're talking about is what are the actual specifics of the test? So take a look at that, kind of put it into one small Word document, or you can find it online, but I put them into a Word document so it's easy for you to find. So our test, May 11th, which is the first one, Pacific time, 9 a.m., which is pretty traditional, nothing new there. All right, exam timing. Students will have 25 minutes to read and respond to question 1, and then 5 minutes to upload their response. After uploading the response to question 1, students will have 15 minutes to respond to question 2, with an initial 5 minutes to upload their response to question 2. Once their response to question 1 has been submitted, they cannot go back to it. So, pretty straightforward online testing format. You'll have a certain amount of time, 25 minutes for the first question, and then 5 minutes to upload your answer, whether that means taking pictures of your written work and submitting those online or scanning them. So again, make sure you've practiced that and you're familiar with the online browser or the secure online browser so that you can complete that in your 5-minute window. All right, so two questions. Let's talk about question 1. It's 25 minutes. It's 60% of the weight of the exam. So question 1 is more heavily weighted, obviously 60%, and it's longer, 25 minutes. And they're calling it the long free response question. Okay? So this question assesses students' ability to do the following. And there's 4 bullet points. And I'm going to read the bullet points and then interpret what I think they mean. And then as I talk about the question, I'll refer back to how I think each part of the question is hitting those bullet points so we can really focus on what the heck they expect you to be able to do. And how that's going to be different than traditional exams for this course. So, bullet point number 1. Analyze representations of physical situations. Okay, what the heck does that mean? Analyze representations of physical situations. Representations can be many things. They could be a free body diagram. They could be a position, velocity, or acceleration time graph. They could be a force versus time graph or a force versus position graph. Or they could be equations that we would get by using Newton's second law, F equals ma, or torque equals I alpha. So they're either going to be graphs, diagrams, or equations. I think that's what they mean by representations, and they're going to want you to analyze them. And so we'll look at what that looks like. In the example problem they provided, they have you analyze equations. They don't really expect you to know where the equations come from. They only want you to analyze them. And that's where I think it's a little bit different than the traditional test, where in the traditional test, they want to see you maybe derive those equations from the physical situation. And most of the points then are awarded for your ability to write down the correct representation of the physical situation. It seems like they're going to focus more on just can you analyze it, and I think that has a lot to do with the ability to grade the question, because they're also doing remote grading, which instead of grading kids' algebraic work, they want to see more of the actual interpretation of what the equations mean physically, as opposed to a more detailed algebraic or mathematical derivation. I think that's also for testing security, because if the question is just like derive this equation, then it's pretty easy for kids to just show each other how to do the math and then push that onto other students. Where if you're analyzing an equation, you're actually having to give a more thorough your explanation of what the equation means and where it comes from. A little bit harder to cheat there. So, bullet point number 1, long question, analyze representations of physical situations. So expect to be given a graph, a diagram, or an equation, and then answer questions on what those things are telling us. Okay. Bullet point number 2, determine scientific questions and methods. I think what that means to me is, do you know when to apply conservation laws or not? Like in this situation, is energy going to be conserved? Is momentum be conserved? And how is that going to affect the outcome of the situation? Like in the example problem, they have a student give an interpretation of the representation, and then you analyze whether you think that is correct or not. So was the method a good method or a bad method? So bullet point number 2 to me is a little more vague. It's pretty open-ended. Determine scientific questions and methods. So basically, are the scientific methods and questions that they present valid or invalid? Not really sure. This one's still a little confusing for me. Analyze quantitative data represented in graphs. I feel like this should be an easy thing. Most of the students in this class are really good at math or in calculus. So this is going to be, like I said, again, almost linking back to bullet point number 1, analyzing graphs and quantitative data in graphs. So really make sure we brush up on our position, velocity, acceleration, time graphs, how to go between those using slopes and areas, and how to read those graphs. Also, I think a big thing will be probably force versus time graphs that relate to impulse, and force versus position graphs that relate to work and energy. Those, I think, are the main types of graphs I've seen in previous AP problems that will probably then show up again. So knowing how to read a graph, knowing what the slopes of each graph means, knowing what the area of each type of graph means. Y-intercepts every once in a while become important, but usually the focus is area and slopes of those different types of graphs. Determine an explanation for or a scientific argument. This is going to be one of those questions that we ask a lot in the regular physics class, and that usually shows up at like part D or E in an AP problem, where it says, you have an option of, here's a situation, is this quantity greater than, less than, or equal to, explain. That's like what I'm getting out of the 4th bullet point, develop an explanation or a scientific argument. They're either going to want you to make a claim about their claim, greater than, less than, or equal to, and then give or develop an explanation of why you chose what you chose. The example problem they give that they shared does that right at the end. It's a pretty common format we use in the regular physics class and that I use during lectures and whatnot. Is this going to be more than this, less than that, or are they going to be the same? Who's going to win the race? Are they going to tie? Explain your answer. So that's the first question, and they're 4 bullet points. I'm feeling pretty good at this. It's a little different than normal because it's focusing more on analyzing questions and giving explanations, and not so much as deriving mathematical equations. So that's where that's at. Okay, next part. Corresponding. So this is their explanation or in description of the thing. Long free response question with increasing emphasis on analyzing and explaining the physics concepts represented by representations and data. Question will have less emphasis on pure calculations due to exam administration security protocols. See question 3 on 2017 AP Physics 1 exam as an example. So that's kind of like what I've been talking about. As opposed to focusing less on your ability to set up equations and manipulate equations, which a lot of the free response questions are, and then determining, either a number or an expression as your final answer, it really looks like they're going to go for more of interpreting and analyzing and explaining. So a lot more words are going to be used in this question than math in the past. So that's cool. I think that makes sense. Physics shouldn't always just be a math class. It should be a physics class. So getting you to analyze and explain, I think, is a good push. Let's see. Units available. I think we already talked about that, or I put that information on the website. We're only doing units 1 through 5. We were in the middle of unit 5 as defined by them. I call it unit 6, but it's whatever. We were in the middle of our rotation unit when we closed school, so we're going to need to do some hard work here in the next coming days to kind of polish that up and then do a bunch of review. So only units 1 through 5. And then the exam will not include Unit 6 and 7, but because school is closed for the remainder of the year and graded required work, we'll go over Unit 6 and 7 remotely as our remote learning for the rest of the year in the same format. I'll put some videos together, some lectures, some demonstrations, and like push out some WebAssign that will be created to finish out the remote learning for the year as we do Unit 6 and 7, which is gravitational, Newton's gravitational law and Kepler's laws. So planetary orbits, how things move. It's a fun unit. Should be interesting to do remotely because it's already hard enough to study the planets and the stars when you can't do labs with them. And then the last unit is oscillations and simple harmonic motion. So that'll be kind of fun. We'll send my daughter off the roof with a bungee cord and we'll watch her bounce up and down or something. Yeah. Other course specific info. AP exam, formula sheet. So basically the last part of this just says like you still get your formula sheet, you still get a calculator, even though it does say that everything they're going to ask you to do should be able to be done without a calculator, but you can still have one. Again, going back on the emphasis is going to be more of, I think, analyzing and interpreting and explaining, so a lot more words as opposed to a lot of quantitative calculations. So they're basically saying you shouldn't need a calculator, but you can have one. Okay, so that's that question. So let's talk question 1. Here's the example. I think it's interesting because they gave us an AP Physics 1 example for the APC course. The AP Physics 1 is the algebra-based course, where obviously the calculus-based course. But because I think of the change of doing less of a mathematical question and more of an analysis question, that kind of makes sense to me. And I think as I talk through the question, it'll make more sense to you too, because instead of having you derive these equations, they just have you interpret what they mean physically, as opposed to knowing where they come from. So yeah, so that's where we're at. So let's see. We'll edit this part out. So you got a stick. Here's our stick. It's got a pivot. This is a top-down view of the question. So basically you have a stick on the table that can rotate in a horizontal plane, and we're going to throw a disc at it. So here's the disc. It's coming in with some velocity. Here's the center of mass of the stick, and we're throwing it at some distance x away from the pivot point. So kind of think of, we're looking down at an air hockey table, and there's a stick that's able to pivot at the air hockey table, and we're sliding one of those air hockey pucks towards the stick, and it's going to hit. Alright, so that's kind of where we're at. This is definitely an angular momentum problem, which we hadn't covered yet, and I will definitely cover this type of question in subsequent videos, because it's actually pretty important. But again, like I said, this question is all about analyzing the equations, not really knowing where they come from. I'll obviously, show you where they come from, so the equations will make more sense. But again, all this question is doing is asking us to analyze it. So here we go. I'll read the prompt. The left end of a rod of length d and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot, as shown above. Point C marks the center or the midpoint of the rod. The rod is initially motionless, but is free to rotate around the pivot. A student will slide a disc of mass m toward the rod with velocity v, perpendicular to the rod, and the disc will stick to the rod a distance x from the pivot. The student wants the rod disc system to end up with as much angular speed as possible. Okay, so we're sliding this disc at the rod. We want the rod to spin as fast as we can, meaning we want to give it also the greatest acceleration that we can, which requires the greatest torque. Yeah, that's the basic situation. So, part A. Suppose the rod is much more massive than the disc. To give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C, at point C, or to the right of point C? So point C is in the center. It's the center of mass. So if it's a really big stick and it's a really small disc, where should we throw the disc? At C, boom, towards the pivot point, less than C, or further out near the end of the rod, greater than C. And I mean, like I said, this is an analysis question. You don't really need to do any math here. The correct answer is to the right of C, because that will generate the greatest torque. And that's it. That's really all you need to say. Hitting the stick furthest from the pivot point is going to generate the greatest torque and the greatest acceleration, giving it the biggest speed. So, simple, right? I've also posted the question with the scoring guide next to the video. So again, if you haven't looked at those, maybe look at those as we're going through this video. And then briefly explain your reasoning. So there's a box for me to check that says to the right of C, and then I have a little box that I can fill in with my explanation. Okay? Boom. On the part B, on the internet, a student finds the following equation for the post-collision angular speed, omega, of the rod in this situation. And they give the equation. Regardless of whether this equation for an angular speed is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation for the angular speed have the expected dependence as you reasoned in part A? Okay, so the equation is, again, you may have no understanding of where this equation comes from. It comes from conservation of angular momentum. We'll go over that. Super, actually not that complicated once we get a basis for what angular momentum is. But really all they're asking is, does this equation fit with our answer to part A? And our answer to part A was hit the stick furthest from the pivot point. And this equation has a dependence on x. The bigger x is, the bigger the angular speed will be. You don't really even need to know about angular momentum to answer the question. You just got to be a good math student. So if x is bigger, the speed will be bigger. Easy. So there's a box for me to check that says yes. So I check yes. That gives me a point. And then I explain that x is in the equation, and I understand there's a direct relationship between omega and x. So again, going back to our bullet points, this is that first bullet point in our specifics for question 1, analyze representations of the physical situation. They've given us an equation for the physical situation, and we analyzed it. X is directly dependent on omega, so we're good. Part C, another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with another equation. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Yeah, this one's, again, it's just analyzing. I think this goes back to the fourth bullet point, develop an... Okay, not sure what happened there with my camera. Made it click. I don't know. Maybe I haven't really been recording this whole time. That would suck. So anyway, we'll pretend like that didn't happen, and maybe I'll be able to edit that out. So part C is, again, it's focusing on developing an explanation and a scientific argument. They give you an equation that's wrong. You're supposed to identify why it's wrong. So there you go. Part D. For parts D and E, do not assume the rod is much more massive than the disc. Okay, so now assume that the rod and the disc are about the same size or have the same mass. Immediately before colliding with the rod, the disk rotational inertia about the pivot point is mx squared. So they give you the equation for the inertia of the disk, and its angular momentum with respect to the pivot is mv naught x. So they give you the equation for the angular momentum. Again, they're not asking you to derive it, they just want you to analyze it. Derive an equation for the post-collision angular speed of the rod. Express your answer in terms of. So here, they are actually having you do a little bit of math. Imagine that. So they've given you all the things you need to know. It actually makes it a pretty simple calculation since this is from AP 1 and it's the algebra-based class. So they've given you all the variables. It's pretty straightforward. You have to do like one step of algebra to do that part. So again, not a lot of mathematics, more analysis and explanations. Okay, again, all right, part E. Consider the collision for which your equation in part D was derived. Except now suppose the disc bounces backward off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disc bounces off of it greater than, less than, or equal to the post-collision angular speed of the rod when they stick together? And there's your greater than, your less than, and your equal to, and to briefly explain your reasoning. So this goes back to like bullet point 2, determine scientific questions and methods, and develop explanations of science. So more explaining. So basically they're saying, what is the difference between an inelastic collision and an elastic collision as they've changed it up? The initial prompt was that it was an inelastic collision and they stuck together. The last part of the question is to say, hey, what would happen if they bounced off each other and it was an elastic collision? How would that affect the speed? This is basically the ball at door question that we started with in the momentum unit and talking about the difference between these types of collisions. And the elastic collision is going to generate the bigger change in momentum for the disk because it's going in positive and then it's coming out negative, and that'll be a bigger change in momentum for the disk, which means there needs to be a bigger change in momentum for the stick. So the elastic collision will give it a greater speed because of the greater force, the greater torque, the greater change in momentum. All of those are great reasons there. But again, I think even though they gave us an AP 1 question, which at first I was a little skeptical of, like, man, why are they giving us an algebra question, an algebra-based question for our example instead of like an old C question. And I think that's the big difference, is that the focus is going to be on analyzing and explaining, not setting up equations and doing algebraic steps. So there you go. That's question 1. Question 2, which is if you read the specifics, short free response question, 40% of the test, 15 minutes. This question assesses students' ability to design and evaluate a lab experiment using graphical analysis of data to find physical quantities and identify physical sources of experimental variation. They're going to give you a lab question. This makes me super happy. We spend most of our class time, I feel like, doing labs and crunching data and making graphs. So this should be something that hopefully you guys feel comfortable with. So 40% of the exam is going to be a lab-based question that's 15 minutes. Their explanation, similar in structure to experimental design, physics C question, question 2 on the 2012 example. So that's the example. Like I said, here it is. It's linked next to this video on the website, so you should take a look at it as I talk about it. This one's really straightforward. I feel like if you can't do this question, you didn't participate in class. So here it is. It's a really basic conservation of energy question. You get to design your own lab. This is literally one of the labs that we usually do in the regular physics question, where we just say, go choose your own adventure and design a lab that converts transfers energy from one type to another, gravitational to kinetic, elastic to gravitational, whatever. So that's basically what they have you doing here, but it's a little more specific. So here you go. 2012, question 2, lab-based question, Physics C. You are to perform an experiment investigating the conservation of mechanical energy involving a transformation from initial gravitational energy to translational kinetic energy. So, they want you to design an experiment where something has initially gravitational energy and then it has kinetic energy. You're going to roll a block down a hill. You're going to drop something off a house. This is pretty straightforward, right? The thing's going to start up high and it's going to have speed at the bottom, and you're going to show that the energy is conserved. Okay, you're given the equipment listed below. All the supports required to hold the equipment and a lab table on the list below indicate each piece of equipment you will use by checking the line next to it. So they give you a bunch of equipment. This part I always think is kind of funny, especially when you read the scoring guide. As long as you use the equipment in your explanation and you check the box, you get the points. So, I don't know, for me, let's see, there's a track, there's a cart, there's some string, there's a meter stick, there's an electronic balance, there's a stopwatch, there's a set of different masses, and a lightweight, low friction pulley. For me, I'm going to use the cart and the track. I'm going to have my cart on the top of the track, and I'm going to let it roll down the track. I'm going to use the meter stick, and I'm going to use the stopwatch because I know I need to figure out the kinetic energy at the bottom, and I need a meter stick and a stopwatch to measure velocity. I also need the meter stick to measure the height of my track. So, and I need a cart so that I have an object that moves. All right, part B. Outline a procedure for performing the experiment. Include a diagram of your experimental setup. Label the equipment in your diagram. Also include a description of the measurements you would make and a symbol for each measurement. All right, that's pretty straightforward. Draw a diagram with your variables on it. You look at the scoring guide. It's pretty straightforward. One of the examples in the scoring guide is exactly what I just proposed. You're going to put your cart on the top of the track and you're going to let it go downhill. Okay, so there it is. So you're going to outline a procedure. So my procedure would say something like, let cart roll down track with height h. Use the meter stick and stopwatch to measure the velocity of the cart once it's at the bottom of the ramp. That's it. Give a detailed account of the calculations for gravitational potential energy and translational kinetic energy, both before and after the transformation in terms of the quantities measured in part B. So I'm going to measure the gravitational potential energy using mgh, so I needed to measure h. I'm going to measure the final translational kinetic energy using 1/2 mv squared, so I need to measure the v at the bottom of the ramp with my meter stick and my stopwatch. Then I'm going to set those equal to each other. The reason why I did not choose the electronic balance is because I don't actually need to know the mass of the cart. It's going to cancel out in my equations. So, that is my detailed account of the calculations. mgh equals 1/2 mv squared. After your first trial, your calculations show that your energy increased during the experiment, assuming no mathematical errors. Give a reasonable explanation for this result. So I think what that means is that your final kinetic energy somehow was greater than your gravitational potential energy. So if I didn't make any math mistakes, there's two things I can think of that would do that. Number one, I pushed the cart down the hill instead of letting it go from rest. So therefore, the experimenter did a little extra work, giving it more energy than the initial gravitational. So that would be one explanation. You push the cart down the ramp as opposed to letting it go. Another maybe explanation would be you didn't measure the height of the ramp correctly, so it actually started out lower or higher, no, lower than you measured. So if you can't use a meter stick, that would happen. But there you go. So that's that. Part E. On all other trials, your calculation shows that energy decreased during the experiment, assuming no mathematical errors. Give a reasonable physical explanation for the fact that the average energy you determined decreased. And then they give you this huge hint. Include references to conservative and non-conservative forces as appropriate. So that's a huge hint that they wanted you to talk about non-conservative forces, basically friction. So the answer to this question is super easy. You just say the cart had friction on its wheels, and that took up some of the energy through heat or work and dissipated it. So if I'm saying mgh equals 1/2 mv squared, my gravitational equals my kinetic, what I've done in that analysis is I forgot about the fact that friction is always acting on every physical situation we ever use. You can't just ignore it all the time. And that's really all they want me to say there in part E, is that my initial calculations did not account for friction, therefore my final energy is less than my initial energy, which happens in every experiment ever done, because that's how friction works. So, lab-based question. Super excited about that one. I feel like those are usually pretty easy for kids to do. Keep it simple. Don't go and try to design some crazy experiment that uses all of the equipment. They give you a whole bunch of stuff. I'll go over some other ones of these as we move forward and some other examples. They gave us the 2012 one, which I think is one of the more straightforward ones that are out there, lab-based questions, which kind of makes sense for the format we're dealing with here, right? So they're going to want to hear you, hi honey, they're going to want to hear you talk about your procedure, and then a little bit analysis of like maybe why your procedure did or did not work, which is what points D and E are for. Why would the energy maybe increase? Why would it maybe have decreased from your expectations, and explain those things. Super excited. I think that question and those type of lab-based questions usually go pretty well for students, or my students in the past. Yeah, okay, so that's the exam. You have 2 questions, a 25-minute long one that's more analyzing a situation as opposed to doing a lot of derivation. Even though the example they gave us did have us do a little bit of derivation, it was a pretty straightforward one. And then a short answer question that's 15 minutes and 40% of the exam. I feel like you guys will do really well on those, and I'll go over a bunch of examples as we move forward too. So I think that concludes the first, whatever this is, lesson video thing. Excuse me. Again, take a look at the specifics, take a look at the 2 example problems and the scoring guides. Email me any questions that you have about any of that, because that's where we're going. That's where we're headed. Yeah, I miss you more than I thought I would, to be honest. The first few weeks of this was just kind of like, all right, we're at home, no big deal. We'll get through this. We'll be back in school. With the realization that I won't get to see a lot of you, or any of you, before graduation. It hurts. It hurts here. Yeah, you don't get into teaching to talk to a camera. Not Jimmy Kimmel here. So, hopefully this works. I'm going to go figure out how to edit all of this into some sort of cohesive, non-nonsense, and I'll make another one with some cups for later, and I'll show you the cups now. Thanks for coming in today.